Hello and welcome to session 4, Reactive with Node.js, which is going to be presented by Clement Escoffier and Alykiotis. So they'll be on in a minute, but first I need to tell you about tomorrow's workshops. If you want to register for them, there is still space. If you go to the page in the agenda down the bottom of the page, you can see the workshops for tomorrow. And next, we're just going to have a quick word from IBM, Call for Code.
Over the past 3 years, Call for Code has proven one simple truth. Technology, with the right deployment ecosystem, has the power to solve the world's greatest problems. I'm Ruth Davis, Director of Call for Code, and I'm thrilled to announce that the 2021 Call for Code Global Challenge is officially open. Now in its 4th year, Call for Code has inspired 400,000 developers and innovators from 179 nations to create tech for good. We are always on, we are open source, and we can't wait to see how you will answer the call. This year's Global Challenge theme is climate change, an issue that touches so many of us in different ways around the world. We've identified 3 sub-themes, each aligned with the United Nations Sustainable Development Goals to help inspire you to build life-changing technology solutions. They are clean water and sanitation, zero hunger, and responsible production and consumption. You can find more information about these themes along with resources and technical tutorials to help you get started at developer.ibm.com/callforcode. This year, we've expanded the Call for Code Global Initiative to address a greater scope of activities. These include spot challenges to address urgent and unexpected societal issues facing global citizens, Call for Code for Racial Justice, open source project contributions, and solution deployments. The Call for Code Global Challenge winning solution will be awarded $200,000 with a number of other prizes at the regional and university level. The top solutions will have the opportunity to deploy their technology in the communities with the greatest need, with help from IBM, the Linux Foundation, and our partner ecosystem. Form a team, choose a clear problem to solve, and start building. Visit developer.ibm.com/callforcode. Commit to the cause, push for change, answer the call.
Hey, welcome back. So next up we have Reactive with Node.js, presented by Clement Escoffier and Alykiotis. Oh, I knew I would get this wrong. I'm so sorry, Alex. From Red Hat. Alykiotis is a software engineer at Red Hat and a Node.js developer. Before joining Red Hat, Alex was a university student at the University of Perez, studying computer science and machine learning. More recently, he focused his efforts on tools that help with deploying Node.js applications to OpenShift and Kubernetes. Clement Escoffier is a senior principal engineer at Red Hat, and he's a Java champion. And he also acts as a React architect at Red Hat. So I'm going to hand over to you, Clement.
Thank you, Katie. So hello, I'm very happy to present today with Alex a reactive system with Node.js. We are going to see in this couple of minutes what is reactive, what is a reactive systems, why it's interesting. But after all the blah blah, Alex will show you well, how it looks like in terms of code with a very nice demo. So, but first, Alex, do you want to introduce yourself?
Yeah, thank you, Clement. So, Hello, everyone. My name is Alykiotis, and I'm software engineer at Red Hat. I work in the Nodeshift project, where we do cool stuff with Node.js around OpenShift, which is a Red Hat Kubernetes flavor. If you're interested, look us up at nodeshift.dev. You can find me on Twitter at @Alykiotis, and some totally random facts about myself. I'm a massive Formula 1 fan, and apart from JavaScript, in my free time, I really like to play around with the Rust programming language. That's me, really. Clement, do you want to take over?
All right, thank you, Alex. So my name is Clement Escoffier. I'm senior principal software engineer at Red Hat. I do a lot of reactive things. I'm acting as a reactive architect. I did a lot of Vertex in the past. Today, I'm doing a lot of Quarkus, and I'm really focusing on event-driven architectures. And we will see how this type of architectures are related to reactive. I wrote a couple of books. The first one, Building Reactive Microservices in Java, can be downloaded for free from the Red Hat Developer Program. So you go on Google, Red Hat Developer, you log in, and you can download this book for free, and plenty others. And another one, Reactive Systems in Java, is not yet published, but you can get an early preview from Aurelie. I really hope, and my publisher too, that it will be done by the end of this year. Okay, as you can see from this book, I'm more a Java guy, but before going really on the Node.js things, I will try to explain what is reactive and why we do reactive. So why? Well, the reason behind reactives come from distributed systems. Since the 60s, we tried to build distributed systems and we failed. At the beginning, a distributed system was what? It was because a single machine, didn't have enough CPU, memory, disk space, and so on. And the idea was simple. Let's connect multiple machines so we can, virtually reach unlimited CPU, memory, and resources, because we will have access to all the resources from the other machines. On the paper, very well. In reality, yeah, it's another story, because as soon as you cross the process boundary, you are in the dark side of distributed systems. Packet loss, message loss, network disruptions, failures, bugs, and so on. And yeah, it's very hard. And even if the technologies have changed to build distributed systems are doomed to fail. CORBA, RMI, SOAP, web services, REST, HTTP, gRPC, and so on, all protocols, all things that are great, but they're always, hard to do. They can't hide the complexity of distributed systems. You need to embrace that failures are part of the game. So you can say, yeah, but in the recent years, a lot of work has been done at the infrastructure layers by cloud provider, Kubernetes, or containers to ease the construction of distributed systems. And that's absolutely right. No, it's only half of the journey. Well, it's not because you can create ephemeral resources that building the distributed systems will be easier and the same, more robust, more reliable, and so on. Actually, you put a lot of pressure on your applications to manage the dynamic availability of all the resources you have created. Another thing, especially around containers, it's not because a container is a box and you can put anything in a box that you should do it. Your boxes, your containers will share a common infrastructures, CPU, memories, and so on. So that means that if you have a couple of greedy containers running side by side with your very nice and cool applications, yeah, you are not going to perform well because all the resources have been assigned to these other containers. So what does that mean? That means that before going inside a container, you need to understand what it means. And that is not only about isolation, it's also about sharing and increasing the deployment density. And for this, you need to have a model, a development model, an execution model that fits this world. And this model will be to use resources efficiently, to use non-blocking I/O, and so on. And then you can say, hey, but Node.js is exactly this. And yes, Node.js is a runtime that make a lot of sense in a container. It's using non-blocking I/O, use a few number of threads, so we'll use the resources efficiently. Okay, another thing that changed around distributed systems is how we use them. Over the past 5 to 10 years, things are completely changed. Since the beginning of my presentation, I believe that most of you receive notifications on your phone, on your laptop, and so on, mails, text. The thing is, we are not getting the information. We are not pulling it anymore. We push the information to you, and that's a big change in how we are building and interacting with the users. So we need a way to push. Also, things like IoT or mobile and the whole mobility world is completely changing how we interact with things. There are devices, they never sleep. So you can send requests at any time in the day. So it's a lot of data to handle. It's a lot of notification of events, of requests to handle. And your distributed systems gets a lot of stress. And over the past 5 years, we are seeing an explosion in terms of events. A lot of things are now going from the classical request-reply mechanism to event-driven architectures. Because of IoT, because of mobility, because of notifications. Well, there is plenty of reason why you want to do that, and we will see why in a few minutes. But first, well, what reactive? Because I explained a little bit the why the distributed systems are hard, but what is reactive and how it's going to help? Well, if you Google reactive, you will find plenty of words associated with this. Reactive streams, reactive systems, reactive messaging, reactive programming, and so on. It's often associated with another set of words like back pressure, non-blocking I/O, already mentioned that one, functional programming, and so on. So let's be clear. The important part is reactive systems. Reactive systems is an architectural style to build better distributed systems. It's been defined by the reactive manifestos, and it's a model for building distributed systems focusing on responsiveness, resiliency, and elasticity, and using a message-driven approach to interact between your components. Everything else, it's just details. Reactive streams, reactive programming, nice, interesting, but they're just tools. What you want to build is a reactive systems. You can build reactive systems without reactive streams or without reactive programming. So what are these reactive systems? Well, as I said, it's an architectural style. Your components, when building a reactive systems, are going to use asynchronous message passing to interact. So you are going to send messages to virtual addresses. You don't know if there is 1 subscriber, 10 subscribers, 0 subscriber, or this number of subscribers consuming these virtual addresses evolves over time. This is the elasticity part of reactive systems. Another thing is resilience. The fact that you can have multiple subscribers behind a virtual address means that if one dies, another one can take over. So you have some kind of built-in recovery. Another thing is that any modern messaging brokers, such as MQP or Kafka, have some kind of retention or durability support, meaning that even if there is no subscriber, it's not lost. It will process it once one becomes available and so on. So if you can have elasticity and resilience, that brings you to the next level, responsive. So that means that your system is going to handle the load, the request, the messaging, even when facing failures, resilience, and even under fluctuating load, the elasticity. It's not doing that simply using a traditional code. It needs to be efficient and answer in a timely fashion. Efficiency means that you need to take care of the resources that are located to your process. Remember what we said about containers. This is exactly this, using non-blocking I/O, not a lot of threads, and so on. And timely manner, meaning that you will always try to answer in a maximum amount of seconds, depending on the system, of course, but at least to have a clear contract with the user so he knows what to expect. So the kind of system we want to build is such kind of system here, where you have lots of messages, push to devices, machine learning, auditing, and so on. And that's actually really easy to use now and to build because of all the technologies that has been delivered. But you may say, well, right now, I'm using HTTP and it works fine. Well, yes, but the problem with HTTP-based microservices is that there is some kind of coupling that you may not necessarily realize. The first is representations that you exchange between your microservices or your services. It's often a JSON, but do you use a schema? How do you make the schema evolve and so on? These questions have been fixed in the messaging world using schema registry and so on, so you can evolve and follow the evolutions. The second thing is uptime coupling or temporal coupling. That means that if one of your service die, well, it tends to cascade and reduce the availability of all the services that access to that service that died, meaning that at the end of the chain, your users get disappointed, and you don't want to disappoint your users. You want to be responsive. So as you can say, well, but we can use circuit breakers, right? We can isolate those features, monitor the interaction, decide if the service that we're calling is there or not. Well, but we're living on the cloud. How many instances of service do you have? 1, 2? Are they collocated? How do you configure a circuit breaker? What's the timeout? What is a sensible default for the interactions? The dynamic world of the cloud that we mentioned at the beginning, great at the infrastructure level, but at a burden on the application level. That's it. How do you configure this? You need to continuously adapt and monitor this interaction, decide what is the best timeout at that very moment, how many instances do you have, and so on. This is very hard to tune, so you get even more problem with this. While on the other side, messaging solved it, well, actually 25 years ago. Almost, yeah, messaging started almost at the same time as the first version of HTTP. It was existing before, but started to be popularized 25 years ago. And we have a lot, well, different characteristics. First, by default, it's going to use non-blocking message spacing. So non-blocking I/O, very efficient and so on. You can have request reply. We have elasticity, as I explained, and resilience, as I explained too. It has more. We can model message streams, event sourcing, CQRS, request reply, publish subscribed. All those patterns, especially publish subscribe, are very hard to get right using HTTP because, well, it will introduce some coupling, which here you have not. So if one of the subscriber die, not a problem. The other one will continue getting the messages. And if the died consumer come back, well, depending on the message technology, it will restart from the last message or only get the new messages. This notion of data address that becomes data in motion is key today. We have seen that with machine learning and so on, but what we had before, data warehouse, data lake, and so on, are really evolving more as a data river, where you need to process the data on the fly. So, yeah, well, you probably have seen that or heard that already. I'm talking way too much, way too fast, and you want to see some code. So before going to see this demo, we'll introduce it very, very briefly. We are going to use the Reactive coffee shop to demonstrate what are the reactive systems, what are the limits of HTTP, and how to build reactive systems with Kafka. We use Kafka here, but we can use any other modern messaging protocol. So if you want to see this demo, you can go directly on GitHub. I will give this URL again at the end of this presentation. Now, Alex, your turn.
Yeah, thank you, Clement. So here I've got my terminal and I have a couple of tabs open. Just I'll go through them briefly. This tab actually will spin up a Kafka cluster. We use Docker Compose for that. This one is running the service that actually takes the orders and also provides us a dashboard on port 80, as you can see over here, and I will show you later. The next one is the HTTP client that prepares requests through the HTTP, as Clement said before. And here is the Node service, which is a barista actually that uses all these asynchronous messaging between Kafka to do the job. So since I'm on the Node client, I will briefly show you the code that we're running. We're just using Node RT Kafka as a client to communicate between Node and Kafka. Here we create a consumer, pretty stuff, and also we initialize a producer. When our consumer is initialized and ready, we start listening for order events from the orders topic. And when our producer is ready, we are actually starting to consume messages, and we prepare the beverages and send it back to Kafka. So we'll notify everyone else that they're ready. And then here we do some error handling. pretty stuff. So let's quickly head back to the demo. Here I'm going to show you the HTTP method of communication. So this simply simulates the case where you go inside a coffee shop, there's a queue, you wait there for your turn, you order a coffee, and you wait there in line until they can prepare your beverage. And when you're done, the next person can order, and so on and so forth. So here I'll put my name, and I'll choose like latte, and I will place the order. So the important thing here is that I can only order one thing at a time. Here says the status failed, but we don't really care about it. The important thing here is that you can only place one order at a time. Cool. I'll switch now to the message in Kafka one, and I will order an espresso or something, and I will create a bunch of orders. So now you can see that I can do multiple orders at the same time, and the Node client actually goes and processes them. Cool. Now, let's say now another example I want to show you is what happens if, let's say, the barista wants to take a break. So let's go and close the barista here. So we have no one to prepare our coffee, but there's no problem because we have Kafka. So I'm going to order a bunch of frappuccinos. And the cool thing here is that I don't lose the orders. They're just there waiting until the barista comes back. So let's say that the barista comes back. I will npm start the barista, and as soon as the barista comes alive, you see here our orders get prepared. Cool. Now the last thing I want to show you is what happens, let's say, if there is a rush hour. So we need multiple ones. It's simple as open a new tab and npm start another one. Let me clear this out so you can see it better. Let's say again, name's Alex, and let's order a bunch of hot chocolate. And here you see that we have two baristas now. We have Ava and Zach preparing our orders. The distribution is not 50-50. It depends on how you configure your Kafka. And that was pretty much the demo. We can go back to Clement now to finish off the rest of the presentation.
Yeah, thank you, Alex, for this great demo. So just to summarize what we have seen, well, the first thing is that we have seen the resilience part of the reactive system. So if we have no barista or if a barista crash, we are not losing the orders. And losing our coffee, we all know that it will be pretty bad. But here we have the retention strategy or retention policy of Kafka that keep them. And as soon as the new barista will be available, it will continue and get the orders ready, which is what we actually want. The second thing is elasticity. So here, Alex started a second baristas manually, but if you're running on the cloud, you can use auto-scaling capabilities or write your own operators that will scale if you are behind the set of orders. So there is multiple strategies to do this. And once the rush hour is over, then we can kill a barista, and we are back using the right amount of resources. So here we see a couple of things. We have the elasticity, we have the resilience, we have the efficiency. We only use the resources when we actually need them. It's all based on non-blocking I/O, so we really build a distributed reactive systems. So again, to summarize, reactive is all about architecture. What you want to build is a reactive systems. It's not about using reactive streams or reactive programming and so on. No, so the goal is to build a better distributed systems which use asynchronous message passing, which has elasticity, resilience, and provide a responsive endpoint, responsive service to the users, answer in a timely fashion and efficiently, especially on the cloud. At the end, you will get a better distributed system, more robust, also more efficient. You will increase your deployment density or decrease your cloud bill if you are using a public cloud provider. So it's really key in modern architectures. One thing, as Alex shows, that Node.js is great to implement these architectures. It has all the characteristics you need. It uses non-blocking I/O. It's all asynchronous. It's containerized well, which is not always the case in any language or framework. So it has everything you want and you need to build such kind of systems. If you go back to the demo, you will see that you also have the Quarkus version of the demo that has different properties. It's a Java stack for the cloud, for Kubernetes, and you can combine them. So it's kind of pretty cool to see them combined. Today the demo was using Node.RD Kafka. We are thinking about switching our recommendation to Kafka.js, as they both have kind of the same features. However, there is things that are a little bit more deep in terms of Kafka, typically rebalancing and things like that, where Kafka.js is a little bit better. But yeah, we are turning that. Pick the one you prefer, the one you are more familiar with, and that will be great. And I wanted to thank you for your attention today. If you want to see these demos, the code that Alex showed you, it's all on these GitHub repositories. You have the Quarkus and Node version side by side. It has also the instruction to deploy it on OpenShift. And so if you use Oracle IBM Cloud, you can deploy it. Also, if you're interested by Node.js and wondering how to do a couple of classical pattern or architectural pattern, Reactive systems, not only things like circuit breakers, Kubernetes deployment, and so on. I recommend you to check the second links about the Node.js reference architecture that Red Hat is working on, and it's updated very regularly with new patterns, with our recommendation on how to make your days easier, because these patterns that we are publishing there, we really have done them in production and testing them. So thank you again, and that's the end of this presentation.
Thanks, everyone.
Thank you so much, Clement and Alex. It was a brilliant talk, and the only thing I'm not quite so sure about is killing off baristas, which you talked about at one point.
Yeah, I may have issues with that. Yes, I agree. Yeah.
So, well, thanks very much. For the next session, for those of you who are registered for the workshop with Matteo Collina, you'll need to go to the link in your email. So there's a Zoom link in your email that you'll need to access. For those of you who are not registered for the workshop, we've still got content for you. If you head over to the agenda and click on the link for the importance of finding the true work-life balance, you'll see Lind Ward, and she's going to be taking you through that. There's still time to register for tomorrow's workshops. The details are on the IBM agenda page. And remember, you'll be able to catch any of today's sessions that you may have missed via the IBM site or via the Nearform YouTube channel. Thank you again to all of the speakers so far today. And I'm going to head off now. So thanks very much for being here. Cheers. Bye-bye.